teach it anyway.
No?
Why did you do it?
Why did you change your mind?
One time, the lazy one time.
So where we at? Did we talk about what do you do when we find a limit on a curve, right? What do we travel along? We talked about that. Do we travel along the x-axis? No, right? What about three-dimensional, right? From what direction, right? Did that. We talked about that. We talked about how many paths. It's infinitely many paths, right? Okay. All right. And the two major problems are infinite number of paths to get to our point. And the other major problem is if you want to prove that a limit exists on the surface at that value, then you want to prove it along all those points, paths, right? That's the problem. We don't want to do that, right? It's easier to show that it does not exist, right? Right, that's what we're doing, okay? And did we do this example? Feels like we did.
Yeah.
We did that example, right? So what happens if you get the same limit along the x and y path? Okay, we have not done this one. I don't feel like we've done this one. Number 3. Okay. So, right. So what's happening is, what we're trying to do is, what you do is, let me just go back to an example, okay? Before I read all this stuff to you guys, okay? That's what I hate about not finishing a lesson. When I don't finish the lesson, it's hard for me to get back on again for some reason. All right. If I do a direct substitution into that function and I get a number, okay, that means the limit exists. Does that make sense? The limit exists at that point because I'm going to get a number, okay? But if I plug in that 0, 0 and I get an indeterminate form, then we got to prove that it does not exist. We try to prove that it does exist or does not exist, right? The easiest way to do is prove that it does not exist. And so the only way, and it's the easiest way to do that, right, is pick a path, right? You eliminate the x path, travel along the y path, right? And see what and travel along the y path to this point, okay? All right, and then see what your limit is. See what you get, okay? It's like one-sided, like almost like a one-sided limit, all right? And then you eliminate the y path, travel along the x path, right? Going towards that point, and you see what you get, right? If you get if you come up to two different limits, that right there proves that the limit does not what class? Exist. Make sense? Right? But what happens if that doesn't happen? What happens if, here's the problem though, what happens if I, travel along the x path, travel along the y path, and they do equal? Does that prove that the limit exists in all paths? No, there's only two paths. What do you do with that? What do you do then? Okay, that's our next focus. Okay, what do you do then if they both equal? All right. So what happens if you get the same limit along the x and y path? Well, this is the first thing you do. Try x equals 0 and y equals 0 paths first. If the first step does not work, choose two paths. If the first step does not work, choose the other paths. Man, that doesn't make sense. Number one, I'm not working out, that makes sense. Number one, be certain that the point AB is actually on your path. Okay. And number two, try to substitute so that degrees of numerators and denominators become the same. Okay? And number three, always use either x equals 0 or y equals 0 as your first path. I'm repeating myself over and over again. But when I show you this will make more sense to you, okay? So here's an example. You got this 3xy, okay? And xy is going to 0, 0. So I know if I plug in 0, 0 into that function, that's an indeterminate form. Okay? And so that means I have to prove that the function, prove that the function does not exist, because that's going to be hard, right? Okay, to prove that. Because if it did exist right there, it would give me a limit, okay? Or we could use L'Hopital's rule, right? L'Hopital's rule, and you know, when you remember when you had indeterminate form, you used L'Hopital's rule, and then you keep doing L'Hopital's rule till you get a limit, right? Problem is, some of us don't know what you got to do. Use a partial differentiation. A lot of us don't know that. I see a lot of us. Maybe all we got to do here today, we can just shortcut through this. I won't do that. Okay, but if we did know that, then that's what we could do. But that's the skill that's coming up next. Okay, the next sections. All right. Okay. So what do we do? Well, we first said, okay, let's go along x equals 0. In other words, in the sense we're eliminating 0. Okay, all right? And so, exactly, so in other words, you're just like you're eliminating those x's there, right? And if I do that, okay, what's going to happen? I'm going to get a limit as y goes to 0. I should have nothing but y's, right? And those 3's are just constants. They can go away. We don't need those 3's. I'm going to have y over y squared. Okay? There you go, exactly. I did a bad job there. If x is 0, right, then this whole thing's going to go to what? 0. Good job. Right? Now, now do not, what you don't do, this is where you got to be real careful, okay? So if I could spend, if I mess this up in front of you guys, we could spend 30, 40 minutes as to why the heck would you do that. I want to do that, okay? I'm glad you caught that, because when I plug in that 0 into x, this whole thing turns to what? 0. Don't even apply the limit. Don't even apply y goes to 0. Because it already tells me, right, that 0 divided by y squared is what? 0. Does that make sense? Don't apply the limit. All right? It's already 0. Automatically a 0. That make sense? Okay? All right? So now along y equals 0. So that means the limit as x approaches 0. Right? Well, same thing. You're going to get a 0 on top, right? And you're going to get a 3x squared on the bottom. Okay? Don't apply the limit because we already got the top 0, so it's just what? 0. Look what happened, right? They're saying what? Hey, these are equal. Well, we just talked about it, that does not prove that the limit exists, right? Okay? So this does not prove that the limit does not exist. Okay? So what do we do? Okay, what if this happens? This is what you're supposed to do, okay? If this happens, right, you get the same limits equal to 0. The same limits equal the same. They're equal to the same limit along these two paths. That does not prove that this limit does exist, right? This does not prove the limit does not exist, okay? Then what you do is what you do is this, okay? I'm just going to start working. You know that y is equal to, let y equal f of x, right? Okay? Or let x equal f of y, okay? So in other words, I'll say along, I'm going to pick a path along y equals x. All right? I'm going to pick a path along y equals x. This is what you do. Let me just get to the point, okay? What you do is, all right, I got to find the limit somehow. So let me eliminate a variable. Let me eliminate a y. Let me eliminate the x. Does that make sense? So I can go from, I just have nothing but x's or nothing but y's. Okay? I'm going from what? Implicit to explicit form. All right? Okay. Now, how do you do that? Strategically, you look and say, okay, look at the higher powers. Okay? My higher powers are what? Squares, right? Okay? By looking at these higher powers, that helps me to determine what y should equal to. okay? And I always choose x. I always try to choose y, change y to x. Okay, you can go the other way around. X equal to y, it doesn't matter. But I always try to choose to change y into x. And so I look at the higher power and I say, okay, if I make y x, right, then this is what's going to happen is I'm going to have 3x squared plus what? X squared, which is going to give me 4x squared. Okay? All right? And that works because if I make y x here, I'm going to also get an x squared. Because what I'm trying to do is eliminate the variables. Okay? So I put it in one variable, right? But at the same time, I want those variables in the numerator and denominator to eliminate. I only have a constant left over. Does that make sense? Okay? So when I pick y equals x, I plug it into that function, right? I'm going to say the limit as x. Now I'm just approaching x equals to 0 because I don't have the y's, right? So x approaches 0. It's going to be 3x times x divided by 3x squared plus x squared. Okay? And what do I get? The limit as x approaches 0 of 3x times x is 3x squared divided by 4x squared. See that? That's what I wanted. See? So now the x squareds cancel out, right? I don't even have to apply the limit. What do I get? 3/4, okay? All right? So right there, so now I can say, okay, look, I found another path. I got 3/4. It didn't equal 0. Therefore, that shows that the limit does not exist, okay? All right? So, you would say so. Okay? 0 does not equal to 3/4. The limit does not exist at 0, 0. You see that? Okay? Make sense, guys? You see what happened? So that's what you do, okay? Everyone understand this step right here? Okay? Now once you do another one, you'll start getting the hang of it. I always look at the higher power, okay? If I can square the x, will that help? Yeah, because if I make yx, right, here, and yx here, this will be like terms, and with the highest power being the square, right? And then this will be a power of x, right? X raised to the power 2, right? And so those x squares will cancel out, and I get a 3/4. Okay? That's what you do. That's the strategy, okay? If this happens. All right? Okay. Let's go to another. Well, that's here's that. That one. I have a lot of examples of this, but I was trying to be strategically wise and picking up, putting it up here on a PowerPoint. Okay? I got a lot of examples.
Is that the U-try?
This actually no, this is no U-try. I had a U-try. And I said, no, it's not. I got so many examples. I said, no, it's not this. Then we get to the point. We go on.
Let's make it a we try.
Let's make a we try. Yeah. Exactly. Okay. Well, look, what's the difference between that one, what we just did, and this one? Yeah, this is 3D versus 2D. Okay? You got a domain of 3D here and a domain of 2D over there. Okay? And so for 3D, this is what you do. For 3D, okay? Paths are now, we're going to use, are now parametric t. Okay? You're going to use the parametric t when you're doing with DBs, all right? Okay? So that's one point. So understand that. Paths are now parametric t. And then here's the next thing that we do. Always choose an an axis as the first path. Okay? And I always choose, again, along x-axis, okay? I always choose that, all right? Always choose an axis as first path. Example, along x-axis, okay? That means I make y equals 0 and z equals 0, okay? And so let's see what happens. If I do that, right, that means the limit. At what point am I going towards your class? I'm approaching 0, 0, 0, right? So therefore, if I make y 0 and z 0, that means the limit x approaches what? So now you could have chose along the y-axis. If I chose along y-axis, it would be x equals 0, z equals 0. If you chose along z-axis, it would have been x equals 0, y equals 0, okay? This is up to you, but I always choose the x-axis. All right? So plug in y into 0, so if I plug in y into 0, well, y into 0, excuse me, 0 into y, right? This is going to go to 0, right? This is going to go to 0. That's going to go to 0, right? They all go to 0, correct?
Yeah.
Okay. And then here, if I plug these y and 0 are going to go 0 to the bottom, so I've got x squared, right? See that? I haven't applied the limit yet. All I did was plug in y equals 0, z equals 0. That's all I did. I have not applied the limit. I don't have to apply the limit because 0 divided by x squared is 0. Okay? Simple as that, right? Okay. So I got the first path, right? Now that's what you do next, okay? So now the next path is along a curve, okay? So along a curve C, all right? We're going to allow x equals t. Okay, let's talk about this for a second before I jump into that, okay? Go look at your example. So I want to use the parametric t, okay? You look at your higher powers, okay? And you say, what can I make t? Can I make t to the first power, t to the second power? Because I'm trying to eliminate, right? Okay, I'm trying to combine like